Okay, so let's look at the solution to this problem. So what we're going to do first is set up our diagram. Now if you remember, the red and the blue cables were conducting current off to the right. So looking at this diagram, we would indicate those as currents going into the page. So the current travelling through this conductor is directed into the page. The blue one was also travelling off in that direction, so we also need to indicate its direction is into the page. Alternatively, the green conductor, its current was coming out of the page. Right, now, the next thing we need to do, because we're trying to work out the force per metre on the green conductor, we need to know the strength of the magnetic field. So if you remember, the two things we need to solve this problem, if we want to know the direction and the strength of the magnetic field in this conductor, we need to be able to use F equals Bill sine theta to work out the magnitude of that force, and we need to use our right hand slap rule to work out its direction. So we need to know the direction of the current in the conductor and the direction of the magnetic field. So, well, there's no magnets anywhere. The only magnetic field that this green conductor is feeling is the net effect of the red conductor and the blue conductor. Now remember, these two are exactly the same currents. They're identical conductors and they're carrying current in exactly the same direction. And so they'll both have a very similar effect on the green one. So let's look at one of them. So if we use our right hand grip rule firstly to work out the direction of the magnetic field due to the red conductor, our right hand grip rule, remember the thumb points in the direction of the current and the curl of our fingers indicate the direction of the field. Well, if we're using our right hand, our thumb's going to point into the board or into the page, and our fingers are going to curl in that direction. So that's the direction of the magnetic field due to the red conductor. Do the same with the blue. Because the current's in the same direction, it will also have a magnetic field line going in the clockwise direction. Clockwise. Now, sometimes people get confused with this, so I'm going to make a bit of an effort here to make sure we're all okay with this. When we know the direction of the magnetic field around a conductor, the field at any given point is simply the tangent to the curve. So this is going around in a clockwise direction. So at this point here, at that point there, the direction would be there. At this point, the direction would be there. And that would be up. The tangent to the point there is in that direction. If I was to pick that point there, it would be off in that direction. And off in that direction. So at any point around the magnetic field, it's simply a tangent to that circle. So if we want to look at what's going on here, then if we imagine a larger circle going around the clockwise direction like this, then the direction would be in that direction there. We shall do it in blue, I think. So the effect of the blue magnetic field is in that direction because the field lines are going around like that. And over here they're pointing up. Looking at the red one, well, the red magnetic field going in the clockwise direction, if we look at it, if we look at the little fields at different points, the tangent there or there would be in that direction, at this point it would be in that direction, and this point would be going up. So if we imagine a larger circle going around like this, like that, we can see that this point here is travelling to the left. So the magnetic field direction due to the red conductor is off in that direction. Now those two vectors will be exactly the same length because this point here we are the same distance from each of the conductors and the currents are exactly the same. And so to work out the net magnetic field, we need to add these two together. But remember, they're vectors, so we need to add them together as vectors. And so we're told, remember we were told, that the magnetic field due to one of these conductors at a distance of 10 centimetres is 2 times 10 to the minus 3 Tesla. So what we've got then, we've got adding them head to tail, this one is 2 times 10 to the minus 3. This is 2 times 10 to the minus 3. The net direction will be off in that direction, and that angle will clearly be 45 degrees. And if we want to work out the value of that, we're obviously going to use Pythagoras since it's a right angle triangle. So we'll call this C. So C squared equals A squared plus B squared, which is going to be 2 times 10 to the minus 3 squared plus 2 times 10 to the minus 3 squared, which equals 4 times 10 to the minus 6 plus 4 times 10 to the minus 6. And it's going to equal 8 times 10 to the minus 6. Therefore, this value here, C, is going to be the square root of 8 times 10 to the minus 6. And the square root of 8 is 2.83. So that'll be 2.83 times 10 to the minus 3. So the net field, that's 2.83 times 10 to the minus 3 Tesla. And so that's the direction of our net field acting on our conductor. There it is there. That's the net field acting on our green conductor. So, what's the direction of the force on the conductor? Well, remember, with our right hand slap rule, our fingers point in the direction of the field, our thumb is in the direction of the current, and our palm is in the direction of the force. So that means that our fingers are going to be pointing in this direction, our thumb is going to be coming out of the page. So if I'm going to try and draw my hand now on top of this, I'll see how we go. So our fingers are pointing in that direction. Our thumb is pointing out of the page, like that. Now, because this is my right hand, if my thumb is pointing towards us and the fingers are off up to the left, then the palm must be pointing down, off in that direction. So the actual direction of the force on the green conductor is in that direction. So, I suppose I should have given you a compass rose to describe that, but if we said that that was, let's call this north, south, east, and west, then that's in the southwest direction. So the direction of the force on the conductor is in the southwest direction. Okay, it's in that direction there. The value of this force, we're going to use F equals Bill. Now, if we think about this, our conductor is running into and out of the page. Our magnetic field is at right angles to the conductor, often this direction, at the southwest direction, and that's the force, and the magnetic field is off in this direction. So everything is at right angles. So certainly the conductor is at right angles to the magnetic field. And so once again, theta is 90 degrees. So it becomes a pretty simple calculation once again to determine the value of this net force. And here it is. F equals Bill. Remember, sine of 90 degrees is 1. So F equals Bill. So it's going to equal 2.83 times 10 to the minus 3. That's the magnetic field strength due to the other conductors. We work that over here. Multiplied by the current. Now the current is 5 amps. That's 5 amps going through our conductor. Now remember, the question was, what is the force per unit length or per metre of conductor? So our unit length is 1 metre. So just multiply that by 1. And so it's going to be 2.83 times 5, which, 2.83 times 5, which is 14.15. So it'll be 14.15 times 10 to the minus 3, which is of course 1.415 times 10 to the minus 2. And that is the force, so it's measured in newtons. And there's our answer.